And good morning once again, cherubs. Okay, so what we're going to look at today is nuclear equations. All right. Now, last time I spoke to you, we looked at isotopes and nuclear radiation, and we talked about the three types of nuclear radiation at the rates. So there's alpha particles, beta particles, and gamma rays. And you've all done your work on that, and you know that the uses of them. However, something extra that you need to do is to be able to discuss nuclear equations and actually show how different isotopes go through alpha decay and beta decay and gamma decay. All right, so you have to actually write out equations. All right, now then, before we get on to that, what we have to look at is what actual nuclear radiations show. So they show how isotopes go through radioactive decay. Now, something that I didn't mention last time was that radioactive decay is something that we cannot predict. So we can't make it go faster, we can't make it go slower, it just happens. All right, it's just something that occurs. And there's no real way of us predicting it. There are certain methods that we can do to control it when you are using radiation or radioactive decay to generate power in nuclear power stations, but we'll get onto that at a later date. All right, so that's what essentially nuclear radiation is. And the pattern that we have to write when we are writing it down is that the atom before, or so the isotope before it goes through decay, the atom that it turns into afterwards, and the radiation given out. Because if you remember, an alpha particle is two protons and two neutrons being lost from the nucleus. So if those particles are being lost, those subatomic particles are being lost, that isotope must therefore change. It can't be what it was originally because something has changed, something has happened to it. And it's the same with beta decay. Beta decay is an electron, but actually what happens is, which is something I mentioned briefly last time, was that it occurs when a neutron in the nucleus turns to a proton. I'll get on to more on that in a minute. And that forces out that fast-moving electron. So again, you've got a change happening within the nucleus. If a change is happening within the nucleus, then you are going to get a different atom or a different element than you started with. And that's something to bear in mind when we're going through this. So there is one golden rule. So the golden rule is that the total mass and the atomic number must be equal on both sides of the nuclear equation. If it's not, you've done something wrong and you need to go back to looking at it. All right, so we're going to start off with alpha decay. All right, so here's an example of alpha decay. You've got an atom of the isotope of uranium-238, okay, and then it becomes thorium-234, and you get an alpha particle being emitted. Now remember that an alpha particle is essentially a helium atom. It's two positives and two neutrons, okay, so it does have a mass of 4,2. Okay, so it's got a mass of 4, but it's got an atomic number of 2. All right, now then, I'm going to go through how you would write this. Okay, so first thing you have to do is remember that you will have a periodic table or have access to a periodic table. All right, however, in a physics exam, anything that you need will be given to you, so you're not expected to remember anything. Okay, so what will happen is you will be given the starting two numbers. Okay, so uranium-238 is 2, 3, 8, and 92. Okay, so you will be given this in an exam. It will then say to you, right, this element has gone through alpha decay. What is it? Okay, and you will actually also get the element symbol. Okay, all you have to do is complete the numbers. Okay, so thorium. When alpha particles are lost, okay, remember that you are losing, okay, 2 positives and 4 overall. So you were losing 4 from this, 4 overall, and you are losing 2 from here. Okay, does that make sense? I hope it makes sense. Because remember that an alpha particle is made up of 2 protons and 2 neutrons. So when an atom emits an alpha particle, its atomic number reduces by 2 and its mass number must reduce by 4. And the reason for that is because helium, which is essentially what an alpha particle is 4 and 2. So remember what I said before, okay? Total mass and atomic number must be equal on both sides. So if this is 238 plus 92, it's a simple maths really. So if this is 238 plus 92, this must be, so 238 must equal this number plus this number, and 92 must be this number plus this number. So let's work it out. 238 minus 4, which essentially we've got here, is 234. And 92 minus 2 is 90. Now just a quick check to make sure that everything's equal on all sides. 238, okay, equals 234 plus 4. Yeah, that works out. 92, 90 plus 2. Yeah, works out nice and easy. Okay, now I'm going to do another example with you, okay, just so you fully get it. All right, so we will do platinum, okay, just off the top of my head. Okay, so platinum, you think, oh my gosh, it's how is platinum, that really expensive jewellery metal, has an isotope? Yes, it does. Most things do have isotopes, but they're not they're not going to be used, obviously, for your jewellery, so don't worry that you're going to be wandering around and giving off radiation. All right. Okay, and that decays down into something called osmium. Okay, so again, just to go through it, all right, so I'll give you a couple of seconds. Okay, you might want to pause it here, work it out for yourself, and then we'll continue on. All right, so first thing I would always do if it's telling you in an exam that it's going through alpha decay is that you would do this. So you get your 4 and 2 straight off, okay? So that makes everything a lot easier. Okay, so then you can just go, right, 175 minus 4, 171, 78 minus 2, 76. Easy as peas, all right? Nothing really difficult there. Okay, now then, this is where it gets a little bit tricky, okay, with beta decay. Okay, so carbon-14 goes through beta decay to give us nitrogen-14 plus an electron, which is essentially what a beta particle is. Now then, when beta decay occurs, a neutron in the nucleus turns into a proton. So a neutron suddenly becomes positive. Now then, what this means is that it then kicks out a fast-moving electron, because don't forget the electrons and protons are opposite charges. All right, so if you... So by turning a proton, turning a neutron into a proton, you've got some extra energy there, and that just releases a fast-moving electron. Okay, you don't need to know exactly why that happens, just accept it. Okay, the number of protons in the nucleus, because the proton number has increased, obviously the atomic number will increase, so it increases the positive charge. Because the nucleus has lost a neutron and gained a proton, the mass doesn't change, because remember, protons and neutrons have the same mass, okay? But what does change is the atomic number. All right, so this is how we would write it. Okay, so we'd go carbon is 14, okay, and it's got that as 6, okay, and it's going into nitrogen. Okay, now then, this is where it gets a little bit complicated, because we write beta, okay, as 0 minus 1, okay, because it doesn't have a mass, but it does have a charge of -1. Okay, now this is where it's going to get a little bit tricky for you. Hopefully it's not going to be too bad. Okay, so this is what happens. Okay. All right, now then, you're thinking, what? How does that work out? Mrs. Matthews, you told us that everything balances. Yes, it does. 14, so 14 plus 0 is 14. That's fine. 6. 7 plus -1, okay, or basically 7 minus 1 is 6. All right, so it works out. All right. Let you digest that for a second. Okay, so we'll do another example. Okay, so we'll do helium. Okay, so helium is 6,2. Okay, this is going to go through beta decay again. So straight off, I always write down the decay first, because then it just makes it easier for me thinking about everything else. So I know, all right, again, in an exam, you would be given the element that it would decay down into. You just got to fill in the numbers. So straight off, that's 6, because that top number doesn't change, because it doesn't change because the mass doesn't change, because a proton and a neutron weigh the same. So the fact that a neutron, has the same mass. So the fact that a neutron has turned into a proton, the mass doesn't change. What does change is the charge, okay? So what happens here is that atomic mass, the proton number, has increased, okay? But again, don't forget, when you add a -1, you're actually taking it away, okay? All right, hopefully that makes sense for you. Now then, quick note for you. New elements are formed during alpha and beta decay because the number of protons change. It either goes down by 2 or it goes up by 1. Okay, it goes down by 2, right, in a alpha decay, and it goes up by 1 in a beta decay. All you need to be able to do in an exam is explain what goes on. So basically just say that an alpha particle is 2 protons and 2 neutrons. So when an alpha particle is emitted, the atomic number reduces by 2 and the mass number reduces by 4, because an alpha particle is essentially a helium nucleus, which is 4 and 2. Okay, remember to say helium nucleus and not helium atom, because an atom would suggest that it's got electrons and it doesn't. It's just a nucleus. Okay. And beta decay occurs when a random neutron in the nucleus becomes a proton. Okay? That's it. Okay, and then in doing so, the mass remains the same because protons and neutrons are the same mass, but the charge goes up by 1. Well, the atomic number goes up by 1. Okay, now then, finally, gamma. You would be pleased to know that gamma has no nuclear equations. And the reason it has no nuclear equations is because a gamma ray is just a way of getting rid of excess energy from a nucleus. They don't change the charge or the mass of the nucleus because it's a wave. It's got no mass. It's got no charge. Okay, so there's no change to the atomic mass or the atomic number of the atom when it goes through gamma radiation. Now then, another little thing to mention is that actually gamma radiation, gamma rays, are sometimes also released when a nucleus decays by alpha or beta decay. All right, so it's not, uranium-238 won't just go through alpha decay. It might go through alpha decay and gamma decay. But because gamma decay doesn't change any of the atomic or mass numbers, we don't have to mention it as far as an equation is concerned, because nothing happens with gamma decay. Okay, as far as that's concerned, it's just energy that's being released. Okay? Hopefully that's that. Well, that's the end, and hopefully that makes sense to you. So what I'm going to do is I'm going to set some work for you on Google Drive as usual. Okay, and I want you to do some practice equations as well. All right, so I will speak to you all soon. Stay safe and take care. Bye.